So here's a comparison of SN1 versus SN2 processes and what to look for. In the SN2 mechanism, the rate determining step is primarily the only step in the mechanism. The rate is equal to the substrate concentration and the nucleophile concentration. The rate of the reaction is best for a methyl, which is better than a primary, better than a secondary, much better than a tertiary leaving group. And the stereochemistry, if there is any, is there is an inversion of configuration. And the SN1 mechanism, there are two steps, at least two steps to the mechanism. The first one is the leaving group leaves. The rate determining step is the formation of the cation, and then we either have front side or back side attack. So the rate determining step is the slowest step, the loss of the leaving group. The rate is equal to the concentration of only our substrate. For the rate of the reaction, since we have to form that cation, a tertiary compound is best, then a secondary, then a primary, then a methyl. And if there is a stereocenter, the racemization of configuration occurs. So here we are back to the summary of what to look for in the substitutions. Make sure you know this page. If you have questions about it, feel free to email as we're going along. Okay, but methyl and primary substrates favor SN2, tertiary substrates favor SN1. Secondary allylic benzoic substrates can react either way, SN2 or SN1, and vinyl and aryl substrates do not react via either mechanism, because to react it has to be an sp3 hybridized carbon. Okay, remember that as you're going forward in this class, that it has to be an sp3 hybridized carbon to get anywhere. Okay, here we'll continue on with part 5 of substitution reactions. And the leaving group, remember, a good leaving group is a weak base. So weak bases are these, weak bases are these down here that are the conjugate base of a strong acid. So things down in here are the things that are good leaving groups. And keep that in mind as you're going along. So here are some examples. We have the nice easy ones, the halides, and then some other ones that we'll talk about is the sulfonate. Here's a generic structure of a sulfonate. And then we have the tosylate, which is a paratoluene sulfonate. They are weak bases because we can draw a bunch of resonance structures for them to stabilize that negative charge, moving it around. Solvent effects. Polar protic solvents are used in SN1 reactions. Polar aprotic solvents are used in SN2 reactions. The polar protic examples are water, alcohols, acids, and amines, things that can have a hydrogen connected directly to an electronegative atom. Polar aprotic solvents are used for an SN2 reaction, and they contain no hydrogen connected to the more electronegative atom, with some examples drawn below of DMSO, acetonitrile, DMF, and HMPA. Oh, and those go via an SN2 mechanism. So in an SN2, or in a reaction, we need to look at 4 things to decide what can happen. So the substrate, here we have a secondary leaving group, so it could be either an SN2 or an SN1, with it being secondary. So we go on down to the nucleophile, we have the sulfide ion. It's a strong nucleophile which favors an SN2. The leaving group, and the third thing, is a good leaving group, the bromide ion. So this does not favor either SN2 or SN1. And then the last one, the solvent, is DMSO, and it being a polar protic favors an SN2 reaction. So with everything favoring an SN2 reaction, we have to look at our starting material. Since it is a stereocenter with bromine ethyl methyl, it being an R stereocenter, our product has to be S. So we either have to draw it differently or think about how we have it here. So if we flip two things and keep two the same, we know we have the opposite stereocenter. So our hydrogen and the sulfur are opposite of the hydrogen and the bromine, whereas the methyl and the ethyl are in the same spot. So our product has to be S in this example. But you should be able to rotate the hydrogen around and back, move the sulfur here and the methyl up here, redraw it, and prove to yourself that this is S. So the sulfur 1, the ethyl 2, the methyl 3, it is S as it goes from 1 to 2 to 3. So here we have some reactions that we can show what kind of things we can form to accomplish whatever we're aiming for. If we want to form an ester, we can use the carboxylate as a nucleophile. If we want to form a nitrile, we use the CN- as a nucleophile. The thiol and the SH, the alcohol and OH and ether and OR. So, and it can be based on what we're looking for in the overall reaction, what we need to get to. And here's the last one from the previous page. If you wanted an alkyl halide, you just have a chloride or a bromide and attack your compound with a leaving group on it. Now remember all of the different things that we've talked about from substitutions, whether you have a strong base or a weak base for A, what type of mechanism it'll be. Primary halides favor SN2, tertiary halides favor SN1, secondary halides depends on, do you have a strong base, strong nucleophile, or weak base, weak nucleophile, whether it's going to be an SN2 or an SN1. The type of solvents you have, polar protic versus polar aprotic, and high temps favor elimination, which we'll get to in the next chapter, and some bases favor substitution. Small ones favor substitution, whereas the large ones like the T-butoxide favor elimination. But we'll get more into elimination as we get into the next chapter in just a little bit. So for the following reactions, identify the type of the reaction, predict the product, and write a mechanism for the reaction. The first one has to be an SN2 because we have a primary leaving group and a good nucleophile, so the mechanism is just going to be the nucleophile comes in, the leaving group leaves, and we're going to get the ether. And the next one, it has to be an SN1 mechanism because we have a tertiary leaving group and a weak nucleophile. So the first step's going to happen, the leaving group leaves, forming the cation, and then methanol will add to that cation, forming our ether. With a positive charge on it, and then another equivalent of methanol will grab that extra hydrogen to give us our final answer. So with the tertiary one, it's an SN1 mechanism. With the primary, it's an SN2 mechanism. So here, draw the mechanism, nucleophile adds to the carbon, kicks off the leaving group, and we get that. In the bottom one, it's going to be an SN1 mechanism, so we kick out the leaving group, forming the cation. Then a methanol adds to the cation. And then another equivalent of methanol grabs the extra hydrogen off of our protonated ether to give us our answer. And I got that arrow a little bit close. And there we have it. In the next page, we have predict the products for the following reactions. And this first one is one that gets a lot of students when they look at it the first time. We have the CH3-, which is a strong base, and OH. So all this is an acid-base reaction where we, in the first step, we form the phenoxide in an acid-base mechanism, and then we add the propyl bromide to form the ether out of it. And in the first step, whoops, got an extra carbon there, sorry. In the first step, all that can happen is the CH3 minus pulls off the acidic hydrogen of the phenol to form the phenoxide. And the second one, we have can draw it as a SN2, where we get the iodocyclohexane. The third one, we're going to kick off the bromine to form the cation. Methanol adds in to form the protonated ether. And then, whoops, not water, methanol will come in to grab our extra hydrogen to get us to our compound. And then the last one, remember this sodium does nothing, so the cyanide can come in and do a SN2 on the iodide, and we get the compound with the cyanide on there. So here we need a strong base to pull off the hydrogen, so CH3 minus, and then do an SN2 on the primary bromide. The CH3 minus is just going to grab one of the two hydrogens off of the nitrogen to give us the N minus, and then that will do an SN2 on the primary bromide to get us there. Okay, the next one we have not done yet, but it's going to need to be an E2, which we'll see in a little bit. And then the last one here, we see that these 5 carbons are these 5 carbons, so we need to add this onto it. We have the leaving group, so all we need is a good nucleophile to do the SN2 on that, so we would need the methyl acetylide to attack that. And then here's a reaction you don't know, but just talking about a nucleophile electrophile. So the nucleophile is going to grab a hydrogen off of the alpha carbon, and then we can draw a resonance structure putting the negative charge on the oxygen. We can draw a resonance structure going back. We know these are resonance structures because of the type of arrow we see here. Those are resonance arrows. And then this is our nucleophile, this is our electrophile. The nucleophile adds to the carbon, kicking off the leaving group, breaking the double bond to the oxygen to get the O minus, which this is then the nucleophile. The water is the electrophile. Put a hydrogen on it, and then we see the OH is nucleophile, and the aromatic compound is the electrophile with the OH. Sorry, I put that E in the wrong spot. With the OH grabbing a hydrogen on the carbon next to the carbonyl, forming a double bond, kicking out the leaving group to get us to our alkene. And then the last one here, draw a mechanism for each of the reactions and show what type of mechanism each one is. This is a tertiary leaving group in the first one, so it needs to be an SN1. The second one, SN2. So in the first one, we don't have a good leaving group, so we need to have the OH get protonated, and then it can leave, forming the cation. And then the Br minus can add to that to form our answer. In the second one, it's going to be a direct displacement of the nucleophile kicking off the leaving group to get us to our product.